So, I am Alexander Holler, and I've been with the Tutoring Center since August 2019, and welcome to our Chem 114 workshop.
My name is Isaiah Morris. I'm a new tutor to the Tutoring Center. I just joined in August of this month. Also here to help you out with this workshop.
All right, so for our agenda today, we're going to cover significant figures, SI unit conversions. We're going to differentiate between atomic weight and atomic mass. We're going to go over isotope notation, oxidation numbers, and naming ionic and molecular compounds. So it's a whole lot we're going to be covering, but it shouldn't be too bad. And then, here's us.
And again, if you guys have any questions, feel free to put them in the chat or speak aloud. Yeah.
All right, so Isaiah, take it away.
Let's start off with some significant figures. So sig figs, well, better known as sig figs, are essentially the number of digits believed to be correct by the person that's reviewing the problem or situation. So they often can vary per problem and have a core set of rules. You can see a nice little example of some here to the right, but we're going to delve more into that in about a slide or two. Next slide, Alex.
Yeah, sorry, I was just letting some people in.
No, all good.
So for the people that just joined a little bit late, we're just starting off right now. We're going over significant figures, and we'll be going over the rest of it. You haven't missed anything, don't worry.
Yeah, no. Yeah, so significant figures essentially come with 4 core sets of rules. They might have some sub rules if you want to rule it that way, but essentially comes down to 4 core things. So when you're dealing with exact numbers, these numbers have an infinite number of sig figs, such as the exact decimal number of 3. The exact number 3. You can put a 0.0000 at the end. It will have an infinite number of significant figures. This is also good to keep in mind when doing unit conversions, as in when you are converting between units and sort of engineering-based problems. Those numbers are going to be exact as well. Just keeping that in mind. The second rule is when it comes to zeros. So zeros in numbers come into play in different ways. For instance, a leading 0 is never important. So say if you were to have a 0 in front of a 4,000, you could do that, but that 0 doesn't count. It's not important. It's the same thing with if you were to do a in embedded zeros going into zeros that are actually within the number itself. If you were to have a 0.403, that 0 in the middle is important, but that leading 0 is not, because it's before the decimal point. However, that embedded 0 is significant. And the last kind of thing about zeros is that trailing zeros are only significant if that decimal point is specified. So zeros at the end of numbers, if you were to talk about the number 4,000, those zeros really don't count as much as if you were to do a 0.400, those decimal points actually do matter. Then going into adding and subtracting with significant numbers. So you essentially retain the same amount of sig figs as the number with the last digits after the decimal. We'll see an example of that again in a little bit. And then coming to multiplying and dividing, you will retain the same amount of sig figs as the number with the least amount of digits. And again, I get this is a lot of information. We'll kind of delve into it in an example in this next slide. All right, so now here we're looking at some examples of significant figures. So I'm gonna kind of bring this up to you guys, or you guys and gals, if anyone wants to help chime in along with this slide. So starting off, we have the number 3, or 3.0 or 3.00. If anyone wants to tell me how many sig figs this number has.
Would it be 1 and then 2 and then 3 for the trailing zeros after the decimal?
So yeah, technically yes. But the way I was trying to show this problem is that it's an exact number. There really was no way to, put that in this line. But 3 would be an exact number. So in this case, if you would like to reveal, it would be an infinite number of sig figs. But yes, you are on track with that. You are definitely correct. So now we're going to the next one. Yeah, no problem. So we have 0.0045. Would anyone like to tell me how many sig figs this has?
2.
There you go. Boom, nice job. 2 is correct. All right, let's go to this next number.
6.
There you go. You guys are on a roll. All right, let's go to the next number. Don't overthink it.
1.
There you go. 1 is correct. But now going on to the next example.
Four.
Yeah, 4. There you go. It's because we have that decimal point at the end. So that means that those zeros after the 4 are going to be significant because that decimal point kind of specifies that. Now we have a few, examples with some equations. So take a few seconds to do this by yourselves. Not meant to be crazy hard. Numerical calculations, just solve that out, starting out with the addition equation, and tell me what your answer is in the correct amount of sig figs.
Is it 8.6?
It is indeed 8.6. Nice job. That is because that 4.2, you have to worry about those numbers that come after the decimal. So considering that the 4.2 has 1 sig fig, whereas the 4.43 has 2, we favor that 1 sig fig at the end. All right, so now we'll go on to the subtraction.
5.21.
There you go. Nice. 3 sig figs. Again, because of that after that decimal point. Nice job. All right, so now we'll go on to some multiplication.
Would it be 99?
It would indeed be 99, right? Because 2.3 has 2 sig figs, whereas 43.2 has 3. And in multiplication, we favor that least number. And then coming on to the last one, division, you guys almost got it.
Would it be 5.77 because of the 3 sig figs?
Yeah, it would be 5.77. Nice. All right. Good job, people.
All right, so moving on, we're going to go over SI unit conversions. And it's something that you kind of just have to do and get a hold of in my mind. And there's some rules of thumb for when you're doing it. So like, for instance, write out your starting units. Make sure that your units are in their base form. So if you have newtons, break it down to meters, kilogram per second squared, stuff like that. So you can more easily figure out what you're trying to get to. And then with each step, make sure that your units cancel out. So for example, this first question here, we have convert 0.836 kPa to PA, which is kilopascals and pascals. So the first thing we're going to do is we're going to write out 0.836 kPa. And then what we can do is we can go check our conversion table and realize that for that, we have 1 kPa is equal to 1,000 PA. And we can write out our units here. Make sure that our units cancel out, and then we can multiply it, keeping in mind sig figs, and end up with our answer here, which is 836 pascals. And the reason that we have 3 sig figs is because these conversions are considered real numbers, so it has an infinite number of sig figs for calculation purposes. So like another example is, let's go from 642.4 liters to meters cubed. So we would write out our unit, our conversion, cancel out our units, and then we have our answer, which would be 0.6424 meters cubed. Now for you guys, I have a question. It's how many cubic inches are in 1 gallon? And then I have the conversions here right underneath it, so it's easier for you guys to write all the stuff. I also have a pre-made chart for you guys here too. So I'll give you guys like 5 minutes for this, and then we'll see where that goes. All right. So do you guys have some answers here now? I see we have one in the chat.
Is it 231?
Yep. So let's write out our units here. We have 1 gallon to 3.79 liters, then liters to milliliters, then liters to inches cubed, and we have 231.24.
Nice.
And then I truncated it at 2 points after the decimal because these are all real numbers, so technically there is infinite sig figs. But a general rule of thumb that I've noticed between a lot of teachers is 2 to 3 points after the decimal is fine. So that's why I just left it at 2, but 3 is also fine. All right.
All right, so kind of not as big of a topic, and crazy as all the other ones that we're covering today, but still very pertinent, is atomic weight versus atomic mass. So, when it comes to reading an actual periodic table itself, you're given various bits of information. Some of it is pretty plain and simple. Some of it's up to interpretation. Some of it you have to think a little bit more. So when we're talking about the atomic mass, if you would like to reveal that for me, Alex. So the atomic mass of an element is the sum of all the protons and neutrons that are in the atom itself. So for instance, carbon 6 protons plus 6 neutrons, that gives you an atomic mass of 12, right? But then when we're thinking about the atomic weight, that is, although it is similar to 12, it is not exactly the same. You can see it's not 12.0, it is 12.011. And that is because it's not just some weird rounding error. It is because the atomic weight of an element itself is actually the weighted average of the atomic mass of all of its isotopes. So some of you may be familiar with, carbon 13, different variations and permutations of, the carbon atom. Those all have different atomic weights because those neutrons aren't the same per element. Per isotope. So that being said, you have to take into account that change in weight, and that's why when we are just given, the blanket carbon, it gives us that rounded atomic weight, so it makes it just easier using in all calculations going forward. And I know at least in chemical engineering department, we use a lot of molecular weight of elements themselves, and usually the atomic weight is what we use.
All right, so going on, we're going to talk about isotope notation. And isotope notation is just a way of writing out how many protons, neutrons, and electrons are in an element. So we would have our base element here, which is X. And then to the top left here, we would have the mass number, which is equal to the number of protons plus the number of neutrons. And the number of protons, sorry, is represented by this Z, which would go in the bottom left here. So, for example, if we were going to have 23 sodium, I didn't put the proton numbers there because I couldn't figure out how to do it in PowerPoint. My apologies. So let me quickly actually open up a P table.
I think you have it.
For everybody. What was that?
I think you have it. You just have to stop annotating.
Yeah. And let me see here. Can you guys see this? It's going to be really small for you guys.
You can see it though.
So for sodium, it has, up here in the top left, you can see it, it has 11 protons. So knowing that it has 11 protons, and then the protons plus neutrons is 23, how many protons, neutrons, and electrons does it have? So, like we said, the number of protons is 11. That means that the number of neutrons would be 23 minus 11, which would be 12. And then because there is no formal charge on the sodium, the number of electrons must be equal to the number of protons. So that would be 11. And now using that, can you guys do these next 4? And then keep in mind that these charges will change, or will make it so that the number of protons and electrons are different. So watch out for this chlorine and then this iron plus 3. Does anybody have the protons, neutrons, and electrons for the chlorine?
Will the proton be 17?
for chlorine, and the neutron be 18, and then electron will be the same as the proton.
Yep. So 17, 18, 17. Okay, now using that same information, what would this next one be? Just chlorine with a -1 charge.
Would you add that -1 charge instead of subtracting it?
What do you mean by add it instead of subtracting it? Adding it to what?
For the electron, for that one.
Right. So you have 17 protons, 18 neutrons, and 18 electrons. Because it has that formal negative charge, that means that there's more electrons than protons. All right, so going on, we have our iron. What would be our protons, neutrons, and electrons for that?
Trying to get tripped up by that formal charge.
So the proton would be 26.
Yep. And we know that the protons plus the neutrons is 36. So we can rearrange this equation to solve for the number of neutrons. We would have A minus Z is equal to N. We know our A and we know our Z, so what would our N be? Yep, 30.
There you go.
And this is where it gets really tricky. How many electrons do we have if it's +3?
29.
No. See, that's where it's a little tricky. See, if it was if it was 29, that would mean that it has a -3 charge because there's more electrons than protons. So that means that this iron would have an overall negative formal charge.
23.
So because this is a positive charge, that means that there is less electrons than protons. There's 23.
A nice way of thinking about that sort of thing, or a nice rhetoric that I kind of use to remember, is that we know that electrons are negative and that protons are positive, right? So if we have a formal negative charge, then that means we must have grabbed a bunch of negative electrons and we're holding on to them. Whereas if we have a positive charge, a formal positive, that means we let go of them. We let go of the negativity. You know, we're just kind of letting go of it, and we're being more positive. So that's a way that I kind of like to think about remembering that going forward.
All right. And then does anybody have this last one?
Would it be 21 protons, 24 neutrons, and 21 electrons?
Yep, exactly. All right, good job.
All right, now we're moving on to oxidation numbers. So a general rule of thumb, you know, there is a general trend when it comes to oxidation states. So as you can see here, we have these various groups of elements. We know that these groups go by columns. So we know that group 1A is the earth metals, and we know that group 2 is the alkaline earth metals, or the rare earth metals, one of those. And then you have that that last group, the 8A group, that is the noble gases. Then you have group 7A, that's the halogens. You know, so thinking about this going forward, all of these elements naturally carry an oxidation state, or the need to either gain or release electrons. So thinking about sort of a thing like hydrogen. Hydrogen has an oxidation state of 1, and you know it's carrying that 1 electron with it. If we think about a Bohr model or a Lewis-Scott model, yes, I'll be explaining more of the rules in a second, but thinking about a Bohr model, how we have those 2 electrons in that first shell, and then we build up to the 8 afterwards, and we build up on those shells of electrons. Well, this is kind of sort of the same thing. Hydrogen only has 1 electron, you know, in its shell, and as such, it wants to do something with that electron, and that's what all of these oxidation states really tell you about a certain element. So if you go to the next slide, we have a few rules. General rules of thumb when it comes to assigning oxidation states. So pure elements are assigned a 0 for their oxidation number. Two monatomic ions will have an oxidation number that is equal to their common charge. So that's kind of what we just covered. No, that's good. That extra bullet point. It's kind of what we
Okay.
just covered. It follows that general trend. Of depending on which group, it kind of depends which what formal. What common charge you carry. If you want to go back to that periodic table again, really quick, Alex, for me. We can see that we increase by +1, +2. Then when it comes to transition metals are a little funky. They got some different rules, so they don't really follow a general trend like the rest of the groups do.
That's not what I wanted to do.
No, that's all good. But as you can see, it goes from +1, +2, +3, and then plus or -4. With carbon and silicon, those essentially vary per situation, and then it goes back down to the -3, -2, and -1. So going back to the rules, yeah, we know that they follow that general trend. We also know that nonmetals can be a little weird. They aren't as clear and cut out as other atoms are. For instance, if you go to, like Alex just said earlier, hydrogen naturally carries a +1 oxidation charge, but it will be a -1 when it's bonded to a metal. So that's one of those special instances you have to keep aware of. Same thing with oxygen. Oxygen is normally carries a oxidation number of -2, but it can be +2 when it's bonded to fluorine. It can be -1 when it's bonded to a peroxide, and actually a -1/2 when it's bonded to superoxides. And going forward with that, the most electronegative atom is naturally assigned to charge first. If all the atoms in a compound are nonmetals, it's kind of like a general rule of thumb. And last but not least, the sum of all of the oxidation numbers in a compound or ion must add up to the overall charge. For most neutral ions, the charge will be 0. But sometimes, you can have NH4 plus, and then that all of the oxidation numbers in that molecule itself have to add up to a +1.
All right, so moving forward, we're going to cover naming ionic and molecular compounds. This is going to be our last section before we open it up for just general questions and anything you guys have for us.
Yeah. All right. So first, talking about naming ionic compounds. So starting off with this, it's good to know that naming ionic compounds comes in strictly 2 phases. Whereas first, you always want to start with the cation. Good thing to remember is that cations come first. Starts with a C. It's positively charged. Often is a metal. In 2 general rules of thumb are if the cation is a polyatomic ion, which essentially just means the ion is composed of more than one atom, i.e., ammonia. You write the name of the polyatomic cation as is. But if the cation is a transition metal, or a metal that has more than one oxidation number, you put the charge in Roman numerals after the metal in parentheses, which, as you can see on the bottom, there are some exceptions to this, but that's the general rule of thumb. Then once you've identified your cation and you know what you're doing with your cation, then you move on to your anions. The anions come second. These are most often negatively charged. They are negatively charged, and they are often a nonmetal. And these anions, as the element, you write the name of the element along with the suffix "ide" at the end of it. And if the anion is a polyatomic ion, you write the name of the polyatomic anion as it is after the cation. So again, like before with the sig figs, this is a lot of information, but this next slide we have a few examples kind of help you guys get into that. All right, so starting off with example number 1. So here we have KBr. Would anyone like to take a crack at trying to name this? I think I should probably potassium bromide. There you go. Nice job. I was going to give it away to you, but yeah, potassium bromide is correct. You start out with that metal, potassium, K, and then you have that non-metal. You have the cation first, then the anion. That anion has a -1 form oxidation charge. That potassium has a +1. They cancel out to create that neutral compound. The non-metal gets the suffix of "ide," henceforth potassium bromide. Let's go to the next one. Anyone want to try this one out? Any guesses? Nothing is wrong, I promise. Okay, you definitely are getting very close, Rosario. It's knowing that this is, if you would like to reveal it for us, Alex, knowing that it is a one of those polyatomic ions that we were talking about. So SO4 is a sulfate, and as such, it carries a -2 charge. So when it's bonded to mercury, it creates mercury sulfate. Now, a good thing to keep in mind is recognizing that it's mercury 1, or Roman numeral for 1. And the reason why is you look at the sulfate and you go, well, it has no subscript of a 2 or 3 next to it, so it obviously didn't carry a charge. Not entirely. Technically, K and Br are K1 and Br1. But when it comes to mercury and sulfate, the mercury takes on that subscript of 2, and the sulfate, because the mercury carried a +1 charge, it takes on that subscript of 1. So that's why you have the Hg2SO4. Moving on to this next example. Would anyone like to take a crack at this?
Is it magnesium nitride?
There you go. Nice job. Yes, magnesium nitride is correct. You had that metal. There you go. Nice job, Haley. You had that first metal, that magnesium, right? We identified that was the cation. Then we had that anion, the nitrogen. You add that suffix of "ide," and there you go, magnesium nitride. Let's move on to this fourth example. Yes, nice job, Haley, but you're missing something.
Oh,
Yeah. No, it's
you didn't see that.
No, go ahead and reveal it. It's
Yeah.
titanium 2 chloride, because titanium is that transition metal and it carries that +2 charge. So that's why it's titanium 2. But nice job. You guys are getting it. Let's go on to this next example. This one's pretty hard, I know. Even the polyatomic ion is pretty rough. Give it another second or two. Should have told everyone in attendance to bring out a periodic table. That was our mistake. But we'll go forward, revealing it is tin 2 silicate. That SiO4 is a silicon polyatomic ion, and Sn corresponds to the element of tin. Therefore, All right, let's go on to the next one.
And don't be shy, guys. It's okay to get it wrong sometimes, because that's how you really learn. Is you get something wrong and you realize, oh, this is where I made my mistake. Let's not make that mistake again. So feel free, even if you're not super confident, to throw your ideas in the chat or say them, and we'll kind of give you guys feedback on that.
Oh my, there you go. That is correct. Magnesium phosphate. I had faith. We'll move on to this next one. Just remember that transition metal rule when naming this one. Yeah, stepping off it earlier, I know that even us tutors included. There you go. That's correct. Mercury 2 oxide. Even us tutors ourselves are keen to get things wrong every once in a while. Actually, more often than not.
Would you mind going over one more time why it's Mercury 2?
Yeah, for sure. So the reason why it has that 2 instead of the 1 like the first one is because of that formal charge that mercury has. So you know how oxygen has a -2 charge? What's happening in this compound here is that mercury is supplying a +2 charge to have that overall charge be 0. So it's called mercury 2 because there is a formal 2 positive charge or +2 charge on that mercury. Whereas with the sulfate, like Isaiah was saying, sulfates have a -2 charge. And in this case, we have 2 mercuries to counteract that, which means that each mercury has a +1 charge. So it has the Roman numeral just 1 there. Because transition metals can have different states. Like titanium isn't always going to only have a +2 charge. It might have a +3 charge. And they show that by having the parentheses around it. Because titanium with a +2 charge results in a different compound than if it had a +3 charge.
I see, that makes sense. Thank you.
Yeah. All right. Nice explanation, Alex. Now on to this third one. Very, very close, but yeah, you're right on there. It is cobalt 3 phosphate. Just get to know. But you guys are definitely on track with this. And then on to our very, very last example. I know that polyatomic ion is.
I have a comment. So since all of these are monatomic ions, correct?
Yes.
So that, okay, that makes sense because the ATE, we have to change the suffix for the ending.
There you go.
Okay. And then is it always IDE, ITE, and ATE
Yes.
for the monatomic? Always? Okay. Thank you.
Yeah, no problem. I'll actually give a hint on this last one. That polyatomic ion is an acetate. Any bites? It's okay if not. There you go. Nice. It's like chromium 2 acetate, but yeah, nice job. All right, that kind of concludes ionic compounds. Let's move on to molecular.
Yeah. Did you guys have any questions before we move on? Because the naming can be really tricky, so.
Can you explain the last one, please?
Yeah, sure. Okay, so the acetate polyatomic ion is C2H3O2, and it carries a +1 charge. So that being said, we have chromium 2, because as you can see, that acetate has that there's 2 of them. It has that subscript of 2. Maybe, Alex, I'm thinking of going into Paint and showing them assigning formal charges and bringing them down when forming together compounds.
Yeah, did you want me to stop the screen share real quick?
Yeah, let me pull up really quick.
Okay, let me see, where is, okay. I lost the little bar at the top that shows me how to stop the screen share, and that is unfortunate.
Let me see. I think I'm able to do it. All right. Do you guys see
Oh,
my
there we go.
Paint? Is my MS Paint visible?
Yeah, I see it.
Okay, awesome. So let's do that example from earlier, that mercury to oxide. I think that's a pretty good one. So we have mercury, right? So we know that it was Hg. Apologies for this. It was Hg and then O. So thinking about our oxidation numbers and that charge that oxygen normally carries, we know that oxygen normally carries that -2, right? And we know that if this is a neutral compound and there's no charge on the compound itself, then everything has to equal out to 0. So then we can kind of take this as if it's an equation. And we're trying to cancel these out to 0. We have this charge right here that we don't know, and we have this charge here that we do know. So we know that 0 is going to have to equal, oh, that's a 6. We know that 0 is going to have to equal x minus 2. This is x. So then we can solve for x where we know that x is also equal to 2. So if mathematic, if mathematic expressions and that sort of visual aspect is really how you learn, this is a good way to make sure that you always get those charges right and can name these transition metal compounds efficiently. This rule of thumb genuinely works every single time. I still use it to this day. Felt like that was useful for you guys to see. Yeah, there you go, Alex. If you wanna take it away.
Yeah, for sure. Let me try this again here. Look at that, I have my little bar back. All right. Let's see, we have a check. Okay. So moving on to naming molecular compounds. So for the first atom, it's always a prefix. There is no suffix. And the prefixes are mono, di, tri, tetra, penta, and just continue on. And if there's only one of the first atom in the molecular compound, the mono prefix is dropped. For the second atom, there's a prefix and then also an ide. So the prefixes, similar to the first atom, are mono, di, tri, and continuing on. And then also another rule of thumb is if the element begins with a vowel, we drop the O or A from the prefix. So if the element was, let's say, oxygen, we would drop the O. I think it's the O from the prefix.
Yeah, I'm pretty sure.
So like for example, here we have N2O4. That would be dinitrogen, and then 1, 2, 3, 4, pentaoxide. See, we're gonna be tetra. Oh, actually, be tetro. Sorry. So yeah, when it's when the prefix. Let me figure out how to word this. So when the element begins with a vowel, you don't drop the first letter, you drop the last letter. So like see how we have tetro instead of tetraoxide? It's tetroxide. So continuing on with that, do you guys want to do these next 5? I kind of have it set up so it's just going to show all 5 at once. So just take like 5 minutes, write them all out, and then we can, kind of discuss them real quick.
Periodic tables allowed. All right, keep that in your back pocket, Rosario. Try to work on the other 4. I guess just to say, I still use everything that we covered in this presentation today. I still use it to this day, even in my upper level courses. Sig figs still come into play. SI unit conversions are everything.
Yeah, like if you're struggling with SI unit conversions, don't feel bad, because like I know I've been doing them since freshman year. I still struggle with some of them, and the way that I've gotten a lot better at them is just, like the examples where you just write everything out, you do more examples, and you just have that conversion table next to you, so you just know what you're doing. And it's just really helpful to have all that.
Yep, and I think, like Alex said, this will be posted to the YouTube channel. So again, you can always rewatch the video if you need, the concepts cleared up again. We'll give it another minute or so. What is the name of the YouTube channel? Is it the FSETC Tutoring Centers? Or FSETC? Let me check.
I believe so, but I don't want to give a wrong answer here, so let me quickly message Brian.
Yeah, and I'm going to do a Google search as well. I think it's Fulton Schools Tutoring. I will send the link in the chat right now. There's also, there's a few examples of some like general like engineering applied questions on there. However, they do also have a video for just kind of teaching you how to access the virtual tutoring, because we do virtual tutoring as well as in-person now. So there's a few videos on virtual troubleshooting, exactly how tutoring goes on here. Yeah, let me put that in the chat right now. There you go.
Oh, you found it.
Also, all right, seems like Rosario has attempted all 5. Yeah, of course, Daniel, no problem. Yeah, no problem, Mona, of course. So Alex, if you would like to reveal the answers and we'll go through them.
Yeah. So it's a little bit of like a wall of text here, but we'll just go through them one by one. So I believe it was Rosario, I think?
Yeah, Rosario.
It said diarsenic pentoxide. So you had the AO, so it was technically incorrect, but you were very, very, very close. And it's just like a little error that, once you start to see more examples, you'll start to catch that more. So because it's an oxide, it is that oxygen. You have to drop the A at the end of the penta. Now, the next one here, we have PCl3, which is phosphorus trichloride. And we don't drop the I because it's an I, it's not an O or an A, so it's fine. And C is also not a vowel, so just trichloride. The next one here, we have, why did it do that? The next one here, we have carbon and then 4 chlorides, or chlorines. So then we have carbon tetrachloride.
Which is very common.
Yeah, you will use this a lot, especially in your lab classes.
Mm-hmm.
You'll notice that it's a very common compound. Then we have selenium and then 6 fluorines. So that is selenium hexafluoride. And then for this last one here, it is water, otherwise known as dinitrogen monoxide. Or why did I put nitrogen? It should be dihydrogen monoxide. I don't know why I put nitrogen. I'm sorry.
My all-time favorite chemistry jokes is dihydrogen monoxide.
I should
fix that. There you go. Never was a problem to begin with.
It's okay.
I have a quick question on those.
Yeah, for sure.
Is there a reason we don't put like monocarbon tetrachloride or monocelium?
Yeah, because if there's only one of the first atom, the mono prefix is dropped. So the prefix mono is not included on the first atom.
Oh, I see. I just didn't read that all the way through. I see. Thank you.
Yeah, no problem. That's a good question. All right. Any other questions?
I have a question.
Yeah, for sure. What is
So
it?
like for the last one, Because I put oxidide, I didn't put mono.
Right. So this is where that mono would come into play because it's one oxygen. You have to put monoxide or monoxide. Sorry. And you don't have the double O because oxide is a vowel. The O is a vowel. So you drop one of the O's. So it's just monoxide.
Okay, thank you.
All right. So is there any questions about the overall presentation? Any comments?
Did you find it useful?
Yeah. What would you guys like to see in future workshops?